welcome you to this lecture on marine hydrodynamics under the NPTEL program. In the last couple of lectures, we have seen how Navier-Stokes equation is used to solve several analyze various flow problems. In particular, our emphasis in the last few lectures was when the flow is unidirectional. In the beginning, we started with a creeping motion where the Reynolds number is very small, and then we talked about unidirectional flow where the convective inertia term was neglected, and in the process the flow was only in the axial direction, one of the axial direction, and in the process we have seen that large number of there is a class of problem which can be analyzed for solution, and solutions are obtained explicitly, and but this class of problem is very few. There are very few such problems where we can get explicit solution. Of course, we have looked into three types of problem. One is oscillatory solution, one is transient solution, one is a steady state solution. However, all these unidirectional flow problems or the fully developed flow problems are limited when the Reynolds, particularly when the Reynolds number is greater than the creeping flow motion, but still they are small. There is another class of problem, but I have talked about in the last class also, that is called where the Reynolds number is moderate in nature. So, basically there is a class of problem where the Reynolds number is moderate Reynolds number, and for this again, as we have already discussed that we have two types of flow. One is the laminar flow, the other is the turbulent flow. We have also depend on particularly the one of the factor which depends whether the flow is laminar or turbulent is the Reynolds number. So, for moderate Reynolds number, the moderate Reynolds number, there is a class of problem for which rarely any closed form solution is available, and we always go for approximate solution. However, large class of problem in fluid mechanics or in real life problems are handled by these various numerical approaches associated with and these are there is a large class of problem. They are basically where in fact either the inertia term nor the viscous term, inertia, viscous and pressure term plays a significant. We cannot ignore none of these terms, and both steady and unsteady. And here both we have steady and case of unsteady. So, here we cannot neglect all this, because even if they are moderate, their role is very important. Flow in pipes, and there are many flows, flow in exits, flow in pipes, and particularly flow near the nozzle, and all these things are very important. Particularly if I look into laminar flows in cavities, flow past a cylinder, sphere, flow along with walls with obstacle, laminar entrance or exit flow, more important in this case of this kind of entrance and exit flow near sluice gate, where there is the gates are they control the flow. And then these are class of problem where the Reynolds number is very moderate, but it covers a wide range of problems in physics and engineering. Then we have high Reynolds number. When the Reynolds number becomes high, as we have seen that for high Reynolds number, I will talk about or we say boundary layer flows. So, what happen, just we know that there are two types of flow, one is laminar or one is turbulent. But what happen, there is a class of problem where just when we have a boundary, just along the any boundary is there or a wall is there, just near the wall the flow remain viscous, the near the wall the flow remain viscous, and beyond this wall boundary, if you look at the flow, any flow here, so the flow becomes inviscid, but in this region the flow become viscous, and then this there is a layer what we call the beyond which this happens, and this layer we call the this distance we call the boundary layer thickness, and then beyond that, and this happens when the Reynolds number is large. Is large. Particularly if you look at the flow in a flow past a plate, we can see, for example, the shear layer exists on flat plate, up to Reynolds number is 5 into 10 to the power 5, and similar such situation occurs in the entrance when you look at the entrance of a duct, entrance or exit of a duct, sorry, if you look at the entrance of a duct, in nozzles and diffusers or at surface of submerged bodies, at surface of submerged body, the boundary layer develops when the free stream Reynolds number is high. Is high. So, this is another example. Here we can see that it is a large number even if for a flat plate, and entrance of duct in nozzles on diffuser, this is in diffuser, sorry, I call it diffusers are at surface of submerged bodies, boundary layer develops. And apart from this, we have seen that there are a large number of problems in which it is observed that the viscous effect are felt just in the immediate neighborhood, as I say that in the immediate neighborhood of the solid boundary. This is the solid boundary and this is just in the immediate, and this distance is very small. In fact, in 1904 in Prantl 1904 on a paper on fluid mechanics, he talks about that the Navier-Stokes equation holds in a very thin layer near the surface of a boundary, and then in which inside which the flow is considered as viscous, beyond which the flow is envisaged. This is inside which, and here the in fact here the both the, and here basically in this region the viscous effect is always comparable with that of inertia effect, and then thin layer near the wall of the solid boundary is this thin layer near the wall of the solid boundary, it was called the boundary layer, and this distance is called the boundary layer thickness. So, it is not, in addition I will say that it is not always that you have to have a open boundary or for the boundary layer to occur. There can be this boundary layer can be also occur in the in a moving fluid region at an interface near a wall, or not only near a wall, at an interface of two fluid, this can occur. For example, I will give you one typical example that how the at the interface of a two that so basically I will just first cite few examples of the occurrence of boundary layer. Again that I say shear layer, where the occurrence of boundary layer occurs, shear layers along flat plate, wedges, aerofoils, flow in duct entrances as I have mentioned, duct entrances, and then we have thermal boundary layer, thermal boundary layers in ducts, boundary layers in porous channel, then we have also, as I said, that at the interface of a two fluid how the shear, one of the example of a fluid region, it is not only on the surface. For example, this example is very important, that if you look at the Gulf Stream, where it departs the USA, the USA coast and crosses the Atlantic Ocean. Atlantic Ocean. Crosses the Atlantic Ocean. There we see the thin layer of a boundary layer, occurrence of a boundary layer is the Atlantic. Atlantic, sorry, outlet equation. So, we also see the presence of a boundary layer, and then with this then that means here in this case the Reynolds number is, although the Reynolds number is large, but there is no turbulent motion, but there is the occurrence of a boundary layer. But again if the motion becomes more beyond this certain in the high Reynolds number regime RE, for certain values of the Reynolds number this boundary layer formation takes place, and after it reaches certain optimum value, then the flow becomes further with an increase in Reynolds number, the flow becomes turbulent. Now, before going to the discuss some of the characteristics of the boundary layer, I introduce two concepts, what is called the order symbol. This has a two meaning. The order symbol, suppose I say f of epsilon is equal to small o of a g of epsilon. If I call this then this is small o, this is order. F of epsilon is of order of g of epsilon, then in that case it happens if limit epsilon tends to 0, f of epsilon by g of epsilon is equal to 0. This is small o, and on the other hand I say f of epsilon is equal to order of g of epsilon if limit epsilon tends to 0, f of epsilon by g of epsilon is equal to is bounded, is equal to some a constant value. So, this is the basic difference between small o and capital O. In fact, while going to discuss the theory of boundary layer equation, the derivation of the boundary layer equation, we will come across this small o and the capital O very frequently. So, this is very important in this concept, and otherwise also in mathematics this is a very important notation, small o and capital O, one has to. In fact, while analyzing various flow problems, always we compare that it is of x is of order y or f x is of order g x. That means, if it is small o, then f x by g x will be 0 as x tends to 0, and if it is capital O, then f x by g x is equal to bounded quantity as x tends to 0. This is what order symbol. Now, I will use this because we know that now I will come to what about the boundary layer thickness, just a basic definition. Let us consider a characteristic length some values characteristic magnitude of horizontal component of velocity u is u infinity, like I assume that this u infinity is kind of a, suppose you have a viscous fluid, and as I have said that beyond the boundary layer the flow is inviscid, and maybe it is a uniform stream, some kind of characteristic length. And then I will discuss a large distance, maybe the u is equal to infinity towards a large distance. So, this is called a characteristic magnitude of the velocity component. Similarly, let L be the characteristic magnitude of length, and depending on the nature of the problem, this L and u infinity are defined. Then, so what happen over this characteristic length, u changes to u infinity. So, that what exactly I mean. And then if I say that if you look at the equation of motion, we have rho du by dt is equal to minus grad p plus nu del square u. If I look at the component wise, there is a convective term here. The first convective term will be, or sometimes I call it the convective term will be before going to the convective term, I will just look at one thing. What will happen here? U del, one of the convective term is u del u by del x. convective inertia term. What will happen? If I put it in the form of order, that is basically the inertia term, then u is of the order of characteristic magnitude is u infinity. So, this will be basically gives me u infinity square by x, it has a characteristic length L. So, u del u by del x is u infinity by L, u infinity square by L. On the other hand, if I look at one of the term of this component of that is the diffusion term or the viscous term. So, if I look at the viscous term, one of the component will be nu del u by or nu del square u by del y square, and what will the corresponding characteristic length? That will be nu, this is u infinity del square u by del y square and by delta square. Why I said delta square? Because I consider delta as the characteristic length along y and x is the characteristic length, L is the characteristic length along x. So, then in that case what will happen, these terms are comparable u del u by del x, because one of the term is here u del u by del x and the other term here is. So, they are of same characteristic length. If they have to have the same characteristic length, that means I will have u infinity square by L will be nu u infinity by delta square, and if that is happen, then what will happen by delta square by L, that is nu by delta square, I brought delta square by L. So, nu by u infinity. So, which gives me delta square by L square equal to nu by u infinity L, which gives me delta by L is equal to, I can always write u naught L by nu root over, and this is like u naught L by nu is nothing but a Reynolds number. So, I can call this 1 by R e root over. So, that gives me del by L, where I consider del is a typical, as I said that this is a typical distance along the y axis, this is the characteristic. So, del by L is 1 by R e. So, from here we can see if del by L is 1 by R e root over. Now, if I say R e is large, if R e becomes very large, this quantity will be very small. So, that means delta will be very large compared to L, sorry R is large, sorry delta is, then this quantity, then if R is large, then this quantity will tend to 0, that means delta is very small compared to L. So, that means this boundary layer thickness is a very small number for high Reynolds number, and that is what, and again this delta will tend to 0 for when R e becomes much greater than 1 basically. So, that is what we have got from here. Now, with this understanding I will derive what the boundary layer equation says. So, we have understood that for large Reynolds number the boundary layer thickness tends to 0, and again if I look at the length scale along the x axis is L and delta is the length scale along the y axis, then delta is much less than L when R is large, and again this relation holds good delta by another thing here also. I will come a little later before coming to this, before coming to that details. Let us look at what happened the simplest boundary layer equation, that is called the in 2 dimension. Let us derive this, and that will clarify many of the questions. In 2 dimension. Let us consider a body boundary. There is a fluid which will be flowing, and then what will happen? as I say that I assume that u is equal to 0, v is equal to 0 at near y is equal to 0, and the x axis is along the wall boundary. So, if I say this x axis is along the boundary of the wall, this becomes my y axis, this is the x axis, and I say that here it is 0. So, there is a fluid flowing here. So, what will happen? Then this distance I call delta. So, what is happening? This is the boundary of a wall, there is a fluid is flowing, the velocity at this tip is 0 and this is a rigid boundary. So, on the wall the velocity will be 0, but between this distance, between this region it is the flow is called viscous, beyond which the flow is, we call the flow as in-vicinity. And then we say that u is parallel to the wall, the velocity component u, basically it is along the x axis. So, u is the x component of the velocity and v is the y component of the velocity. So, what will happen near the, and again when u becomes, because I say u is 0, v is 0, near y is equal to 0. So, and the u from the velocity component u from 0, it will raise to u naught as along the mainstream. When I say along the mainstream, that means within a short distance, that means within a short distance from the boundary, and that short distance I call delta, and this delta I assume that this is the, so beyond which u is equal to u naught. So, u is u naught, sometimes also we call this u becomes, we say u is u naught as y tends to infinity. So, this is what, or I will say we can also say that u is equal to u naught when y is greater than delta. So, that will come. Now, I assume few things. Suppose I assume, based on this I assume the component of velocity u, then t is the time variable, x variable, these are the quantities, rather I will say the quantities u t x are of order 1, and I will say y is of order delta, where delta is much less than 1. If this is the case, then what will happen? Then what will happen to, from continuity equation, if I look at, if you look at continuity equation, we have del u by del x plus del v by del y, because it is equal to 0. If that is 0 and u and x both are of order 1, both u and x are order 1. So, because this quantity is of order 1, this quantity also has to be order 1. And if I say y is of order delta, since because u t x are order 1, so this is of order 1, and whereas del v by del y also has to be of order 1. However, if I say y is of order delta, so that gives me v is of order delta. So, that is one of the important conclusion we have drawn from this, because why I say that I assume there is a, that means along the x axis with a small changes, the changes if x u t x there is a small change, there is not much changes will be affected. On the other hand, it will tend to, they are of very small quantity, but whereas if I say there is a change order of delta, means rather y delta I will say that y delta will tend to 0 here, whereas here u t x tend to 0 if I go by the definition of order. So, B is of order of delta, as u is of order delta, by continuity equation we have got V is of order delta. Now, with this understanding, now let us look into what will happen to del V by del t. So, in the process we have del V by del t, del V by del x, del square V by del x square, because x is of order t x, they are of order 1. So, these quantities are of order delta. On the other hand, what will happen to del square V by del y square, because y is of order delta, V is of order delta. So, this is of order delta to the power minus 1, because y is of order delta, so y square will be of order delta square, where V is of order, and this is this way of defining the order is called relative order of magnitude. Relative order of magnitude, and sometimes we call it as a Roma. In fact, this is very important to derive the boundary layer equation in two dimensions. So, now if you look at the, now let us look at this compare the terms of the Navier-Stokes equation, rather the equation of motion in two dimensions based on this order of magnitude. If you do that, now from Navier-Stokes equation of motion in two dimensions, you have del u by del t. I am just expanding the Navier-Stokes equation, plus u del u by del x plus v del u by del y. This is equal to minus 1 by rho del p by del x plus nu by, rather I will say nu del square u by del x square plus del square u by del y square. And again we have to look at del v by del t plus u del v by del x plus v del v by del y. Okay. So, now if you look at this, let us look at the order of each term. So, V is of order, sorry, this is u is of order 1, t is of order 1. So, this is of order 1, here also is of order 1, here this quantity is of order, because V is there, y is there. So, it is again of order 1, this is of order delta, this is of order 1, this is delta, and again I assume that this is again of order delta, and then nu. Nu is of order delta square, because we have just earlier when we have compared the when we have seen this comparison between nu, I will come to that. So, nu is of order delta square, I will prove that if it is required. Del square u by del x is again order 1, and this is of order 1, whereas this is of order delta square, this is of order 1. So, what will happen if I look at the term here? So, first this is of, if I multiply with this, del square u by del x square is of order delta square, whereas nu del square u by del y square is of order, it is minus 2, is of minus 2. So, in fact, all these terms are of order 1 except the term nu del square u by del x square, which is of order delta square. So, this term is a very small term if I look at the other terms. So, what will happen? We can neglect this term, because delta square will be very small. So, this term can be neglected. If I neglect that, that will give me Then in the same way, so this term is of order delta square. Now, if I look at this term again here, what is happening? This is of order delta, this is of order delta, again this is of order delta, then sorry, this is del p by del y, and again this is of order delta, again delta square, this is nu is of order delta square, del square v by del y square, this is of delta, and this is of order del square v by del x square, and this is 1 by delta. So, if you multiply this is of order delta, delta q, and this is of order delta. So, and then we look at del u by del x, the equation of continuity. You have del u by del x plus del v by del y is equal to 0, because we have this is of order 1 and this is also of order 1. So, if I just look at, I just take the consider the terms which are of order 1 and the terms, and only consider the terms which are order 1, then what it will give me? That will give me the x component of the velocity del u by del t plus u del u by del x plus v del u by del y is equal to minus 1 by rho del p by del x plus nu del square u by del y square. This becomes, and then you have del u by del x plus del v by del y 0. So, this becomes the boundary layer equation in one dimension, in two dimension. And this is what was derived by Prandtl. And in a similar way, we also seen that 1 by rho del p by, because here what will happen 1 by rho del p by del y, because this term we are not taking, this will be of order, is of order delta, and if it is of order delta, that means p, it can be easily seen p is of order delta square. So, that means p is equal to p is 0 and may be neglected, and so p is 0 along the vertical axis. So, what will happen? So, which implies p is of order. So, what we say? So, p can be neglected across the boundary layer. We suggest that p can be neglected across the boundary layer. So, that is because it is of this of so in the process I can call it del p by del y is 0. So, that is on the other hand. So, that means p is a constant. So, which del p by del y means p can be a function of x only, and we normally consider that p is considered as a constant normal to the boundary layer, that means along the x axis. So, if that is the case, then what will happen to 1 by rho del p by del x, because we know that if we have the boundary layer beyond this line u is equal to u naught, and if u is equal to u naught beyond the boundary layer, then from Euler equation, and here the flow is free stream flow. So, from Euler equation we can get what will be 1 by rho del p by del x. From Euler equation it will be del u naught by del t plus u naught del u naught by del x, that will give me minus 1 by rho del p by del x. and here the gravity term is included inside it. So, that is what my del p by del x will give. If I substitute for this equation in the boundary layer equation, that means I will get what I will get? I will get a del u by del t plus u del u by del x plus v del u by del y is equal to del u naught by del t plus u naught del u naught by del x, then plus nu del square u by del y square, and we have del u by del x, sorry, u is equal to 0 equal to b at y is equal to 0 and u is equal to u naught as y tends to infinity. So, this becomes the, and here we have already, I have already told that it will satisfy this equation, u v will satisfy this equation, and also the continuity equation, that is del u by del x plus del phi by del y is equal to 0. So, these two are the boundary layer equation in 2D, whereas these are the two boundary condition. So, these two equation has to be solved subject to these two boundary condition. And now, this is called the boundary layer equation in 2 dimension. Now, I will analyze a few things based on this boundary layer equation. So, I will again go back, just certain observation we will make from this equation. This is from this boundary layer equation. If I look at this equation, this boundary layer equation we have seen, just look at the unidirectional flow. In case of unidirectional flow, we have taken, we have a pressure gradient term, but what had happened there? We had taken the flow, convective inertia terms are neglected. They are neglected, and we had called our flow as u is equal to u by t. Often it appears that as if, but there the fluid was viscous throughout. Here what is happening? We have the fluid is viscous within a boundary layer, but near the wall boundary, but beyond the boundary layer the fluid is in mission. So, this is the basic difference between the laminar flow, one of the basic difference between the laminar flow and the boundary layer flow, boundary layer equation, that is fully developed flow. And then the what I say, the boundary layer equation. Now, I will just some others, let us look at some of the observation, these observations are very important. We have seen that del by L is based like 1 by R e, and that is nothing but nu by u naught L, and this is much less than 1, because R is much greater than 1, as R e much greater than 1. Now, so what we have observed, that the boundary layer is a very thin layer, and it is thin layer, basically rather I will say boundary layer is very thin compared to the length of the submerged body, to the length of the body or the length of the body or whatever of the structure, because del by L is much less than 1. And again here too we have the Reynolds number is large, R is much large. For example, when you look at the laminar flow, as I have mentioned, when you look at the laminar flow past a plate, then our Reynolds number is varies between 10 to the 3 is less than R is less than 10 to the 5, and only when R is becomes, this is for laminar boundary layer flow. On the other hand, R is greater than 10 to the power 7 for turbulent flow. When there is just a flat plate. On the other hand, and here if you look at that, the streamwise velocity here, because streamwise velocity that u is equal to u naught, we call this as the streamwise velocity. Just beyond the boundary layer we have this u is equal to u naught. So, I can say that the streamwise velocity is dominating. Velocity is predominant in the boundary layer flow. Again we can see, because this boundary layer is the fourth point, I will come to that. We can easily see that if you look at V naught by u naught is of the same as V by u, and this is of the nature V is of the order delta, u is of order length, delta by L is much less than 1 we have seen. So, that means what it says, that means the vertical velocity component is much smaller if you look at the. So, that shows that V naught is much less than u naught. That is another observation. Then another fifth observation I will say, if you look at the momentum equation in the y direction, here most all the terms are neglected, except all the terms are almost neglected. If you look at the inertia term, look at the viscous term, or the pressure term, rather I will say inertia term, viscous term and pressure term. All these things are negligible along y axis, and in fact that means even if the mass is basically the inertia term, inertia force, viscous force, pressure force, body force or the pressure force, all these things are negligible along the y axis, only it is predominant along the x axis. So, these are some of the observation what we have. Then we have another observation is that easily we will see that, because when we have seen this problem, we have taken u is equal to 0 and v is equal to 0 at y is equal to 0, and this is the flow is along the x axis, this is y, this is along the x axis. So, we have seen that. So, near a stagnation point, the leading edge, one of the very important point, the leading edge or stagnation point, this leading edge at the stagnation point, where we have seen that in case of aerofoil there is a flow singularity which occurs, and in this situation the leading edge, near the leading edge, rather I will say the boundary layer equations are invariant. are invalid. Here flow is a u is 0, v is 0, we initially describe this and this is the way. So, here the near the leading edge or the stagnation point, the boundary layer equations are invalid. Under in this situation R A is not very large. This is another point. So, these are some of the observations on the boundary layer equation. Now, with this understanding, if I go into solution methods, if you look at the how we look into the solution methods for the boundary layer equation. Because we have earlier seen when we have looked into unidirectional flows, we have considered the flows of transient nature, steady state, either the motion is steady or unsteady, and then we have seen which to apply this flow is oscillatory or non-oscillatory, and one of the method used to similarity transformation method, or we have used, and in the case of we have also mentioned that in case when the Reynolds number is more than that of the unidirectional flow motion, then we can use only approximate methods, that is. But what will happen in case of a boundary layer? On case of a boundary layer, the solution methods what we will use is there are three methods. One is the integral methods, another method is called the self similarity method, and the third method is called the finite difference method. In fact, I will come in detail to this these methods. In brief, I will discuss about this integral method and self similarity method in the next lecture through certain examples. And another thing is that this boundary layer, these methods, this rather I will say boundary layer equations are invalid for they are invalid to deal with the flow near a leading edge, and also the near the separation point, near the point of separation, as we have seen that the shear force will be 0, shear will be 0, and then the free stream Reynolds number is too low when free stream is small. And again this equation will not hold when the boundary layer thickness that means del by L is of order 1, because we have seen that when del by L is only of less than equal much less than 1, then only this equation will hold good, the 2 dimensional boundary layer equation. But if del by L is of order 1, then boundary layer equation as derived will not hold good. So, this is valid, or this is this case it. So, all these cases we cannot apply the boundary layer equation to deal with a flow of this nature. And with this understanding, the next class we will discuss about the solution methods and associated with the boundary layer equation through various practical examples. With this we will stop here.